Hi, let us begin the journey of understanding how magnets work. Okay, so first of all, we consider the magnetic effects on a current carrying loop in a magnetic field. Okay, so this is a rectangular loop, though it doesn't look like one, but let's assume it is. And the field over here is everywhere uh, in the upward direction. Let me make it clear, let me clarify. Suppose this is the x-axis and this is, let this represent the plane of the loop, okay, or no, let this represent the plane of the loop, then and this is the x-axis, then the plane is inclined at an angle phi with the x-axis, okay, and the magnetic field is actually perpendicular to the x-axis like this, okay. So and the current direction is assumed to be like this. The voltage source is not shown, it may be anywhere, it doesn't matter. So we will apply the hand rules to determine the force on the conductor due to the magnetic field and the current flowing, okay. So let us consider this point first. Positive charges flow supposedly in this direction, the direction of current. So by this formula we have the direction of force as V cross B. So V points here, okay, and B points upward outside. So as you can see, when I curl my finger in the direction of B, F points there, so it tends to rotate it like this. This force tends to rotate the coil like this, okay. Similarly, when this current comes here and at this point it goes in this direction, the field is everywhere the same, upward. Again we apply the rule V, let me do it, V cross B. You can see the force is in this direction. It's difficult. V cross B in this direction. So as you see, this force also tends to rotate it like this, okay. It tends to rotate the coil like this, like we saw earlier. The torque can be calculated, and I skipped that calculation. It's actually similar to the way we calculated the torque on an electric dipole, okay. So yeah, here also the torque due to this force and torque due to this force add up, and they give a total torque of the value IBA sine phi, where A is the area of the loop, I is the current flowing in the conductor, like this, and phi is the angle between the x-axis and the loop, okay. And yeah, these forces, here also you can apply the hand rule to find out the direction of force. I is like this, B is again upward, so I cross B is like this. And similarly current goes like this there, so I and the B is upward, so the force goes there. These are equal and opposite, so they cancel. These are also equal and opposite, they also cancel, but that doesn't mean the thing can't rotate. On this loop, though the net force is 0, it will still rotate because this force has a torque about this axis of rotation, and this also has a torque about this axis of rotation. What the net force 0 implies is that the center of mass of this system, in this case the center of mass of the loop, has zero acceleration if the net forces are zero. So in this case, when it rotates, the center of mass will stay at the same position since all the forces cancel and the net force is zero. This actually can be proved by using Newton's laws of motion, which I will do in a later video, but do not bother about that. Okay, so this is it, and the product IA is very important. It's called the magnetic dipole moment mu. You can see that the torque directly depends on the product IA. The greater the product IA or mu, the greater the torque, and so on. We can define a vector mu by taking the direction of mu to be perpendicular to the plane of the loop in the sense determined by the right hand rule. What right hand rule? I mean that by this, that curl your fingers in the direction of the current. In this case it's like this, so the direction of mu would be that given by the thumb, which is actually like this here. Okay, so this would be the direction of magnetic dipole moment or mu. Okay, and you can actually note that the torque is maximum when the magnetic dipole moment is perpendicular to the magnetic field, and zero when mu is parallel or anti-parallel to B. How is that and why is that? Well, uh, when mu and B are perpendicular, that is mu is like this and B was like this, when they are perpendicular, the coil would be like this, vertical. Then you can see that the force times the lever arm would be maximum. To clarify, let me do something. First of all, let me revise torque again. This was that gate. Again, this is the rotation axis, okay, and this is the line of application of force, and this is the distance between the axis of rotation and the line of application of force, called the lever arm. And we saw that when the lever arm is greater, the torque produced by the force is greater and it's easier to rotate that object. And when the lever arm was lesser, the by the same force, the torque produced is lesser, and therefore you need to push harder to produce the same angular acceleration or to produce the same rotational effect. Okay, so the greater the lever arm, the greater the torque. The greater the torque, the faster it moves from rest to rotating at a good speed. Okay, so the torque is maximum when the mu is perpendicular to B. Well, as is written here, the direction of mu is given like this. The current flows like this through this loop. So mu is like this, and when mu is perpendicular to B, the situation is like this. Let this be wait. Yeah, let the pencil represent the x-axis here, and B therefore is perpendicular to this pencil and going into the camera like this. Therefore, when mu was like this, when mu is perpendicular to the magnetic field, it's like this. So the coil is actually like this. When the coil is like this, let me shift it. When the coil is like this, the lever arm is maximum because the axis of rotation goes like this, and the distance between the axis of rotation and the line of application of force is this, the maximum. As we rotate it, the distance between the line of application of force and the rotation axis reduces. See, this distance between the line of application and the rotation axis, and you see as it rotates, the distance reduces. Let's do it again. This was when the mu perpendicular to B. As it rotates, you see that the distance reduces. Okay, and when mu is parallel or anti-parallel to b, that is this is the x-axis, this is the b, and this was the mu. When it is parallel or anti-parallel, okay, then the angle phi between the plane of the loop and the x-axis becomes 0, and when we put 0 in this formula, sine 0 is 0, therefore the torque is 0. So therefore the torque is 0 when mu is parallel or anti-parallel. Anti-parallel is just means that it's aligned opposite to it, and parallel. Okay, so therefore I wrote mu parallel to minus b here. Minus just reverses the direction. Hope that's clear. Well, to summarize, whenever there's a current going through the loop, there's a quantity called the magnetic dipole moment associated with that loop, and that quantity directly determines the torque on the loop when it's placed in a external magnetic field. Okay. Now, the important thing to note is that just like the electric field, uh, wait, yeah, just like the electric field try to align the dipole along the field, the torques try to align it to the field. Similarly, the torques due to the magnetic forces here also try to align the loop in the direction of the, oh sorry, let me say that again. uh, the Yeah, the electric field tries to align the mm, electric dipole along with the field. Similarly, the magnetic field tries to align not the loop but the magnetic moment parallel to it. Okay, just like here it was rotating, the forces were trying to rotate it like that. Okay, so finally when the mu is aligned to the loop, sorry, when the mu is aligned with the magnetic field so that phi is 0, then the torque would be 0 as we saw, and when the torque is 0, the effect that is trying to actually rotate it becomes 0, and therefore the loop is in static equilibrium when mu is parallel to b, that is mu is in the direction of b. Now what does static equilibrium mean? Well, when the mu is aligned with b like this, mu like this and b like this, then if you rotate the coil slightly, the forces built up would be such that they would try to regain the position of the loop. They would try to bring it back like this. So that is what static equilibrium means, and that's when mu is parallel to b. Okay, you can actually check that from the hand rules when you actually move it like this and then apply the sign, these rules I cross b and so on. You would find that the forces built up are such that they try to regain the phi equals 0 mu parallel to b position. I hope that's clear. Now let's move on to how magnets work. Okay,